Welcome everyone. This is week number 13 and we are starting our lecture number 23. So welcome to the course of Fundamental of Econometrics for undergrad level. The previous 2 weeks, if you may recall, was focused on the heteroscedasticity topic. We were discussing in detail the concept of heteroscedasticity, how it causes, what are the consequences of heteroscedasticity. So when the variance is not constant across the given values of the explanatory variable, we have a problem of heteroscedasticity. And then the major consequences of heteroscedasticity is that the OLS estimators are no more blue. They are still linear unbiased estimator, but their variance are not minimum or best. Because of that, we can't trust our T or F statistics. And for those reasons, we see that it's a problem that we have a heteroscedasticity in our data. We also discussed the tests for heteroscedasticity, namely BP test and white test, and we also discussed how we can graphically check for heteroscedasticity. In the previous week, we discussed that how we can solve the problem of heteroscedasticity using some remedial measure. We discussed the transformation mechanism, the use of weighted least square method, and that was pretty much the discussion on the heteroscedasticity during the last week. In week 13, we are going to start a new topic, and this topic is autocorrelation. Now, what is autocorrelation? That's the first starting point for our today discussion. We are going to see the examples from US consumption function. We are going to talk about the test for autocorrelation, the graphical method, the Durbin-Watson test, and the BG test. So these are the topics for the next two lectures of this week, but obviously before starting autocorrelation and all these discussion, I would prefer to give you a small background for that would be helpful to understand this topic. So let me start with a small background. The background I'm going to start is with the statistics concept. Now, don't be surprised when I'm starting the concept of statistics and introducing you to the mean, median, mode, standard deviation, mean deviation, and variance, etc. But this is important to bring it in context. Now, in statistics, when we have a data, we want to summarize them. Normally, we use the univariate summaries. The univariate summaries refers to a single value summary, such as mean, median, mode, etc. listed here. All these are univariate summaries, so that summarize the entire data to a single value. That's pretty much clear, very basic, so I don't want to go in detail to start telling you what is mean or mode or standard deviation, etc. The second inline summaries are bivariate summaries. Now, bivariate summaries refers to the summary of data when you have more than one observation. It's kind of like when you have paired observation, then you use bivariate summaries along with the univariate summary. For instance, when you have two variables such as miles per gallon for a vehicle and the vehicle prices, so this is two variables, and we may be interested in vehicle price, average vehicle price, or average miles per gallon, or the median prices of vehicles, or the median mileage per gallon. But at the same time, we may be interested beyond this univariate summary and would like to have some bivariate summaries. And these some bivariate summary would be like, for example, we may be interested to know how these two variables are linked. For example, if vehicle prices increases, how their mileage per gallon increase or decrease. So it's a kind of like what happens to one variable when the other variable change. So to put it more concrete and complete, I want to say that in statistics, when we have data, we have interest in univariate summaries and also in bivariate summaries if we have paired observations. So now this should be linked with later on discussion about the background I have. Then we have one of the bivariate summary which we call covariance, and covariance refers to one bivariate statistic that indicate that how two variable co-vary or kind of move together. So this is a bivariate statistic. Just like mean, median, mode are univariate summaries or univariate statistic, this covariance is a bivariate statistic, and I'm sure you have studied that in your statistics 2 course. So how we can calculate this covariance, let me show you with this formula. It's listed below. Covariance between two variable x and y is equal to 1 over n minus 1, then summation I is starting from 1 to n, and then we are multiplying two values xi minus x bar with yi minus y bar. If I just focus on the two values of this formula, xi minus x bar, this is the mean deviation for the first variable, the distance of the observation from its mean for x variable, and yi minus y bar is the mean deviation for the y variable. So the covariance is calculated by multiplying the two mean deviations of the two variables for which we want to calculate this covariance, and we sum this product and we divide it with n minus 1. Now once you have data on two variables and you want to see how they covary, you may calculate covariance using this formula, and this formula ultimately result you to a single value. For example, if I have data on vehicle prices as x variable and y variable as mileage per gallon, and I calculated its covariance, so I will be getting a single value, and that single value summarize the co-moment of these two variables. So let me elaborate this further. For example, if I have vehicle prices in thousands of US dollars and the mileage per gallons in miles per gallon, and let's say I have around 100 different kind of vehicles, and I calculate their covariance by the formula listed on the previous slide, and let's say I got the value of minus 20, and then obviously it has the unit of measurement as well, since I'm calculating it from x and y variable. So both of the units get multiplied, so I get minus $20,000 miles per gallon. Now if we go for the interpretation of this minus $20,000 miles per gallon, it indicates that the two variables are negatively linked. That's very clear because the sign is negative. Secondly, the problem is it's difficult that what does this minus $20,000 miles per gallon actually, what does it indicate? Its interpretation become problematic. It's just like it's not telling me if one thing is changing, how the other is responding. It's just giving me a summary number with a complex unit of measurement. Another difficulty or for problem with this measure is, for example, if I start measuring the vehicle price, instead of in thousands dollars, putting the original price, and similarly miles per gallons, instead of I change the unit to kilometer per gallon, this value changes. So that's another problem. So what I wanted to convey is that covariance is a measure, a bivariate summary statistics that measure the co-moments of two variables. But the problem with this measure is that it's difficult to interpret, and secondly, it's sensitive to the measurement scale of the variable. So the problem of the covariance are solved. This problem of the scale and of the interpretation is solved by making the covariance a unitless measure. So unitless measurement is done. How we do that? By calculating the product of the mean deviation of the two variables which we have and divide them with the product of their standard deviation. So all we do is what we solve this problem by dividing the covariance by the product of the standard deviation of these two variables for which we were calculating the covariance, and this gives us a dimensionless unitless measure, and we call this measure the correlation coefficient. I'm sure you are familiar with this formula. You have seen that formula in your statistics course. Here the re-emphasis on this formula was to refresh your memories about this, the origin of this formula and how it works. So I shouldn't be telling you what this formula says because you are very much familiar with that. This is correlation coefficient. This measures the correlation between two variables, so the range is between -1 +1 regardless of the unit of measurement. It's not sensitive to unit of measurements, and when r is +1 it shows perfectly positive correlation, and when it's -1 it's perfectly negative correlation, and r is 0 for no correlation, and normally the values stay between -1 and +1. So remember, this is very important. Correlation only measure the co-moment and the linear correlation between two variables. It does not show causation between two variables. So what does it mean? It means correlation will only tell you that if x variable change, y is also changing with x. Now it is not measuring that since x and y both are changing together, x is causing y, or y is caused because of x, or y is causing x. It has nothing to do with causation. It only measures the co-moment that two variables are measuring, two variables are moving together. So it's a co-moment of two variables, nothing more. So this thing is very important about the correlation coefficient. So you may have been surprised that why I have been focused so much on the background of these concepts which you already know. The reason for that is that I want to link it with some concepts which we have to study in this lecture and onward. So let me introduce you to concept autocovariance and autocorrelation. Now if you understand what is covariance and what is correlation, you shouldn't be facing any problem with understanding the autocovariance and autocorrelation. So autocovariance and autocorrelation is same kind of relation among variable as we have covariance and correlation. The only difference is that in covariance and correlation, we were using two different variables. We were using x and y variable and was measuring their co-moment when we were calculating covariance and correlation. However, in autocovariance and autocorrelation, we do the same thing again. But this time, instead of using two different variables, we use the same variable but measure in two different time periods. So for autocorrelation, when we focus on autocorrelation, we talk about the autocovariances and autocorrelation. Correlation is a better measure than covariance. By same way, autocorrelation is a better measure than autocovariance. So we are going to use autocorrelation more frequently, and we are going to talk about autocorrelation. I will be ignoring the autocovariance part. So autocorrelation is referring to a correlation between a variable late one or more time period and itself. It's like contrast it with correlation. In correlation, we say we measure the co-moment or the relationship between two variables, that how these two variables moves together over a period of time. Now in autocorrelation, we say that how one variable is correlated with the same variable but measure in different time period. One time period or two time period lag. Lag refers to the previous value. So the previous period, like for example, I'm measuring a y variable. So the autocorrelation would refers to the correlation between the y variable measured in period t and y variable measured in period t-1 or t-2. So that's what the autocorrelation is. This is the example, relation of a time series yt, observation in time t with another time series yt-1, so observation of lag period. This is called autocorrelation of order 1. So you can think of autocorrelation of order 2, order 3, or even higher, depending upon if you are measuring the correlation between YT and its second leg or third leg or even higher leg values. The next concept is the measurement of autocorrelation. So how we measure autocorrelation? We already know that correlation is measured with the correlation coefficient. So how we measure autocorrelation? Autocorrelation can be calculated for a y variable, for a time series variable YT with the following formula. If you look at this formula, this is pretty much similar to the correlation coefficient formula. The only difference is that we are representing it with rho and with subscript k. K refers, rho is for correlation coefficient. Subscript k refers to the order of leg, like how many legs I'm considering. If I'm considering YT with YT minus 1 or with YT minus 2. So if it's YT minus 1, this will be just rho or rho 1, and rho 2 could be YT and YT minus 2, and similarly rho 3 could be Y and YT and then YT minus 3 correlation. So, and then if you look at the denominator term here, it's square instead of two variables deviation and then under the root. The reason is it's the same, so when it gets multiplied it becomes square when you contrast it with correlation with the correlation calculations. Now keep in mind, you don't have to memorize this formula or the formula of correlation or covariance which I showed you earlier. The reason is, again, software do these all for you. So pk value like correlation coefficient range between +1 and -1 for perfect positive and perfect negative autocorrelation. So now this is important. Correlation coefficient and autocorrelation coefficient has same interpretation. Both have a range of +1 and -1, and both and 0 value represent no correlation or autocorrelation. +1 refers to a perfect positive or perfect negative correlation and autocorrelation. So when positive autocorrelation happen, it's the case when error in one time period are positively correlated with errors in another time period. So that's the case of positive autocorrelation. Similarly, negative autocorrelation is the case when the error in one time period are negatively correlated with errors in another time period. Now, time series data patterns can be studied using autocorrelation coefficients. Now, you may be surprised why we want to see or why we want to use autocorrelation coefficient. So, the autocorrelation coefficient is very useful while studying different patterns of time series data. Like we can check for randomness, seasonality, or trend in data using this autocorrelation coefficient. So that's a very important measure, and we are going to use that very extensively in our discussion for regression analysis in journal. And in this particular week in particular, you should know that autocorrelation occurs in time series data. It's a time series issue, so autocorrelation too happens in time series. So the pattern can be identified using autocorrelation coefficient at different time legs. So you can find the patterns of seasonality or trends through studying the autocorrelation coefficient at different time legs. We are not going to see that right now or in this particular regression analysis context, but in general, autocorrelation has been very useful. Autocorrelation coefficient in different time periods has been very useful to tracking these seasonality trends or randomness in time series data. We in this particular course are focused on the use of autocorrelation coefficient for measuring autocorrelation only, and studying it in the context of the regression analysis. Now I presume till this stage you have been able to link the terms covariance, correlation, autocorrelation, autocovariance, and then correlation coefficient, and then autocorrelation coefficient. You should be able to tell the difference between the correlation coefficient R and autocorrelation coefficient rho. So now we move to one more concept before we start formally the chapter of the econometrics book, Gujarati book, econometrics by example. And the new topic or the final concept is lag value of a variable. I used the term lag value in my previous slide, so let me elaborate that as well, because we are going to use that also a lot in this 2 to 4 lectures which we have to cover in this week and in the week to come. So let's say I have a time series variable that's measured for 12 period. It's shown from time 1 to time 12, and this is 12 months, January till December. Let's say this is variable YT and it's a sales data. So I have certain product which I am selling. I sold 123 unit in January, 130 unit in Feb, 125 in March, and so on till 160 unit in December. Now what does lag value mean? So let's say I have a variable YT. YT refers to a variable measured in each time period. So T refers to here months. So Y January, Y February, and so on. When I want to calculate YT minus 1, we can calculate lag values manually, which I'm going to show you here. Let's say I want to see what does YT minus 1 mean. I told you that YT and YT minus 1 refers to YT measured in previous period, and autocorrelation is just the correlation between these two variables. So YT I know. From where does this YT minus 1 comes? So, well, I can calculate that from my this original data. So let's say I have a sales in sales in January equal to 123 units. Now the lag value for January would be the value of December, but here there is no value of December, so I will just leave that because I have no old value, so this value would be no value. Then for February I have the sale of 130 units. Now the lag value for this is 123, so for Feb YT minus 1 would be 123. Similarly for March I have a sale of 125 units, but the YT minus 1 would be the value of February or Y measured in previous period, which is 130. So similarly I can calculate all values. For April I was selling 138 product, but the March value would be 125. That would be the lag value for YT. Similarly for May 145 and lag value 138. So all I did is I moved the first value to the second one, and then I continue that repetition. So that's YT minus 1. Similarly I can think of YT minus 2. Now for YT minus 2, when I measure January, so for January I should use the value of November, not December but November. But since I have no value of November, so I will have this no value. For February I should have the value of not January but December. So since I have no value of December, so this will be empty as well. For March I should have a value of January. Since I have the value of January, so I would bring it here. So I have 123. That's the value of January. That's 2 lag. So March, and you go 2 months back in period. For April, you again go 2 months back. So you got the value of Feb, and so on. It continues. So that's the value, lag value for 2 time period. Now, don't be confused that how difficult it would be if you have thousands of data and you have to calculate that. The software have built-in mechanism for calculating these values directly for you. And for the usefulness, why we will be doing these lag values and these autocorrelation, as I told you, autocorrelation is issue of time series data. So time series data have an issue of autocorrelation, we can use it for a number of things. It has a lot of application, so we are going to see that. Now I give you some concepts, some basic concepts that we are going to use very extensively. So I hope you understand that. In case you still have issues, I would advise you to go through this part of the video again and then proceed further with the formal start of chapter 6. So chapter 6 is focused on regression diagnostic 3, and that's the autocorrelation. So now we are formally starting this chapter from the Gujarati book with entitled Econometrics by Example, and it's focused on autocorrelation. So let me start this with the basic assumption of classical linear regression model, in which we have the 7 assumptions that we discussed in pretty much detail. Now I'm not going to discuss these assumptions again and again. I will just focus on A5, which says that there is a no autocorrelation or covariance of error term ui uj given x is equal to 0 where I is not equal to j. Now I already explained you what is autocorrelation, and so if you look at here, covariance or correlation between error term measured in time period I with error term measured in period j. So you can think of error term measured in period t and error term measured in period t minus 1, error term in period t, error term in period t minus 2, because we put a condition that I and j is not equal. So that is the case when this correlation is equal to 0, when error term in period I is not correlated with error term in period j. We call it a case of when it's 0, then no autocorrelation. When it's not 0, then it's a case of autocorrelation. It could be positive autocorrelation, it could be negative autocorrelation. Let me say it again. When correlation, let me say it again, when correlation between error term measured in period I and error term in period j is 0, we call it a case of no autocorrelation. Or when correlation between error term measured in period t and error term measured in period t minus 1 is 0, we call it a case of no autocorrelation. Now let me move further. So when this assumption hold, when we say that the classical linear regression, this assumption of correlation between the error term hold true, we call it a case of no autocorrelation, and that's the requirement, necessary requirement for OLS estimation procedure. However, when this assumption violate, we call it a case of autocorrelation, or we say that our data has a problem of autocorrelation. And obviously we need to check in that what is causing autocorrelation, or and obviously we need to fix that issue with our data. So let me first tell you that why autocorrelation is an issue, why autocorrelation is an issue, and what causes autocorrelation. So let me first, so when this assumption of autocorrelation get violated, this important assumption of autocorrelation or 0 autocorrelation get violated, we call it a case of autocorrelation, and we need to check in for this problem in our data. Now when this assumption violated, there are a number of implications for our OLS estimators. But before going for that, we should look into what causes autocorrelation. So that lead me to the new subtopic, causes of autocorrelation. So let me show you the summary slide of causes of autocorrelation. Autocorrelation may be because of many reasons. Let me show you and let me discuss it one by one. First of all, I will move to the first cause of autocorrelation, which is the inertia. Now what does inertia refers to? Let me explain it. A salient feature of the most economic time series is inertia or sluggishness. For example, if we focus on some major macroeconomic variables such as gross national product, price indices, employment, etc., all these follows the business cycles, and I'm sure you know what does business cycles mean. It's the upward and downward movements of economic activities. For example, because of the circumstances prevailing in the global economy in these days, the global economy is going downward, and everything, all these macroeconomic indicators are going downward as well. So all these macroeconomic variable moves with business cycles. So if we think of the case when the economy starts recovery from the recession, or when we are at the peak of our recession and suddenly the economy starts recovering, if I draw that, normally the economic activity with period of time, we say that the economy moves like this. So think of when the economy is here and it starts recovering, so you're moving upward. What happens then? Most of the time series start moving upward. For example, if we are here, the unemployment would be the highest because the economy is at the bottom. But when the recovery start, when it's moving upward, the unemployment would start reducing, or the employment would start increasing, the production will start increasing, the price indices will start rising, the GNP would start rising. So all these will start moving. So we can say that when we were at the lowest level, when we were here, everything was at certain value, and we can say when we are moving in this range, everything is increasing. So we know that for sure that if a value is a value at this point and at this point, so it's a kind of like these will be linked, or these values would be linked. So you know that when the business cycle is moving upward, these things will move upward. So these are linked, and we say that there is a momentum built into these variables, and it continues until something happens. For example, we reach to the peak, or some policy intervention happens, and that let them slow down again to move in another direction. So in bottom line, the time series variables, the macroeconomic variables, has a built-in phenomena of having issues with being linked with its previous values, and these things causes then autocorrelation, or in other words, when the successive values of the variables are correlated or linked, or when the successive values of the variables are interdependent, then we have a case of autocorrelation in our data. So that's the reasons that the time series variables are having a problem of autocorrelation most of the time. Then I go back. The second cause of autocorrelation that we can refer to is the specification bias. We have been discussing specification bias extensively, but let me show you how it may cause. So let's say we consider the case of excluded variable. For example, we have a true model. Let's say we have a model in which we have three explanatory variable. Y should be function of x2, x3 and x4. However, due to certain reason, for example, not considering the econometric model at a theory level properly, or being unable to identify this x4 variable as being the most important one, or an important variable that should be included in the model, we somehow by mistake or by ignorance do not include that variable in our model, and instead we estimate the model with only two explanatory variable x2 and x3. So what will happen? The excluded variable x4 will be linking with the error term in the second model. Why this happens? This is important to conceptualize. When we say that whatever variation in y happens, that happens because of these x2 and x3 variables, and all other influence is included in the error term. Now there was another important variable x4 which we excluded from the estimated model. So the influence of this x4 variable will be captured by this error term. As a result, this error term will be linked with this explanatory variable. So what happens, the x variable x4 that was excluded, that become a function of the error term, or in other words, this error term is linked with this x4 variable. So as a result, the successive value of the error term will get correlated because of this x4 variable, because x4 in period t is going to be linked with x4 in period t minus 1 in period t minus 2, because it's a time series variable, and time series variable are this is a built-in function of being linked with its previous values. So when x is correlated with its previous value, y is also going to correlate it with the previous value. So as a result, there will be a problem of autocorrelation in your data or in your model. So the second case of autocorrelation is the case of incorrect functional form. So let's say we have a true model in which x2 is a function of y variable is a function of x2 variable non-linearly. So y2 is modeled as yt is modeled as a function of x2 and x2 square to capture the non-linear effect of the dependent and independent variable. Now, due to our ignorance or due to being unaware that these two variables are non-linearly correlated, we model them as a linear variable correlation, or as a linear model, yt being function of x linearly. So what happens again? This x2 square term will be correlated with error term. Why? Because we say that whatever is not included in the model is captured by the error term. So since we didn't include x2 square term, so that will be becoming incorporated or captured by this error term. So as a result, we get a correlation, a kind of a correlation of error term being correlated with x square term. And since x2 is a time series variable and its successive values being linked with one another, we would be facing a problem of error term being correlated with its previous values as well as a result. So this will also lead a problem or will result in autocorrelation. So going back to the main slide, the summary slide, we studied two causes of autocorrelation, namely the inertia and the specification bias, which is discussing the case of excluded variable and then incorrect functional form. Then the third phenomena we can think of is Cobb-Wick phenomena. Don't get confused with this heavy word Cobb-Wick phenomena. Let me explain it very quickly. Cobb-Wick phenomena. Cobb-Wick phenomena refers to the applications of the price mechanism and the responses of farmer productions to the price mechanism. Economists call this phenomena Cobb-Wick phenomena. According to economists, when the price changes, the farmer respond to these changes by their harvest and their supply changes. However, they say when the prices changes, the farmer response to that changes take one period time. For example, if the prices of wheat is high in one period, in 1 year, now the farmer can increase that wheat production in next year only. So in that context, we say that when farmer consider the planting decisions of certain crops, they keep in mind the prices of the last year, or in other words, the current decisions of the crop harvesting depends on the price of the previous years. And we say that it take in agriculture market, the supply do react to prices, but with a lag of one time period, because supply decision here take time to implement. So that's important. We say if the price was higher last year, then only the farmer will increase their production in this year. Or if the prices were higher last year, the farmer can increase their production in the current year. Or the agriculture output responds to higher prices with a one lag period. So this could be shown with some graphical diagram as well. Maybe that can explain it to you. So this is the formal demand supply framework, and we say this is the equilibrium price. Now at a let's presume at a certain period, suppose there were high prices due to low supply last year. So what does happens? Low prices cause rise in prices. That's what low supply causes rises in prices. That's a standard economic theory. And when prices rises, what happens? It's caused to high supply, but the farmer can't do that right away. They have to wait for one period to rise their supply. So we say when the prices were high, they raise the supply. But when they raise the supply in next year, there is an excess supply, and high supply causes the prices to fall. When the prices fall, it causes low supply. So when low supply happens in next period, again there will be shortage and there will be higher prices in next period. And because of that high prices, this cycle repeat again. So we say that the process continue and the prices keep on rising. This is the case of divergence cobweb phenomena. You can think of convergence as well when this cycle gets reversed. So this is a mechanism through which the prices in agriculture market works. Economists name this is a cobweb phenomena. So according to this particular explanation, we said that in cobweb phenomena, this is also one of the major cause for autocorrelation, because the prices the prices or the supply decisions are linked on the previous prices and supply values. So that lead to a problem of linking the successive values of the error terms of these kind of models, and that's leading to the problem of autocorrelation. Going back to the summary slide of the causes of autocorrelation, we can think of the fourth reasons of autocorrelation. That's the lags. So let me explain you. I already tell you what is lag. So we can think of a model, a regression model, in which we say consumption is being function of consumption in period t-1. So consumption today depends on consumption of yesterday. That's pretty much economic behavior. So in this particular model, we can see here clearly that the dependent variable is a variable measured in period t, and independent variable is the same variable measured in t-1, or it's the explanatory variable is the lag value of the dependent variable. So the above equation has a special name. We call it autoregression. We call it autoregression model because this one explanatory variable is the lag value of the dependent variable. So these models are called autoregression models. And if we neglect somehow, if we are unable to include that lagged variable in our model, or if we somehow exclude this variable in our economic model, we may cause error term to capture that effect. It would be also, you can think of the case of excluded variable, but this time excluded variable is not a variable, a different variable, but it's the lag value of the dependent variable. So we call it the case of autoregression, or case of autoregression of order 1, it could be of order 2 or even higher order. So this also lead to a problem of autocorrelation. Then the fifth case is manipulation of the data. So what does manipulation of data refers to? We sometimes do manipulate our data, and that cause autocorrelation. For example, we have data measured on monthly basis or quarterly basis, and we convert that to yearly basis, or from monthly data to quarterly basis. Like for example, dollar values being measured in everyday basis. Dollar to rupee exchange is measured on everyday basis, but somehow you are doing some annual analysis and you required exchange rate for annual basis. So that would require that you take average values of every day and then average it on a year basis. So that conversion may introduce, this is a manipulation of your data, and you are converting daily data to yearly data, and that would cause that may cause autocorrelation in your data. Sometimes we do interpolation or extrapolation of the data, that may also cause autocorrelation. Interpolation refers to a case when you know two values and you somehow try to find a value within that two values range. For example, if I know the value of year 1960 and the value of 1965, so I try to calculate 1963 value using some interpolation techniques. Or sometimes we do extrapolation. So extrapolation refers to interpolation for out of sample data. For example, if I have data for 1960, 1965 and I want to calculate from these two values the values for 1970, so it's a kind of the case of extrapolation. So using interpolation or extrapolation of the data may also cause autocorrelation in our data. Then the sixth one is non-stationarity. That's a very technical term, so let me explain it. A time series data or a time series variable is called stationary if its characteristics. What is characteristics of a time series? The mean, the variance, the covariance. When they are time invariant or when they do not change over time, so we call such time series a stationary time series. Stationarity is a very important concept for time series analysis. That's what we are going to study in our last week of the semester. So I wouldn't throw more light on it, but here I would say when we are dealing with time series data, we have to check whether a particular time series variable is stationary or non-stationary. When a variable is stationary, that's when its mean, variance and covariance is constant over a period of time. We have no problem of autocorrelation. But if there is a non-stationary time series, we may have a problem of autocorrelation in our time series. So this was the causes of autocorrelation, and then obviously the next topic is the consequences of autocorrelation. Like, okay, we know what is autocorrelation, we know what causes autocorrelation, but then the next question is why we are so concerned about autocorrelation. What happens if there is autocorrelation? So the consequences of autocorrelation, there are several listed here. The first one is, which you should keep in mind, that OLS estimator are still unbiased and consistent. Recall that in heteroscedasticity this was also the case. The OLS estimators were unbiased and consistent. So it's the same for heteroscedasticity as well. Our estimators are unbiased and consistent. Secondly, they are still normally distributed in large sample, so nothing to worry. But the OLS estimator are no longer efficient, meaning that they are no longer blue. So they are not efficient, they are not best, they are not having the minimum variance. So that's the reason they are no more blue. So in the most cases, standard error are underestimated. So now these 2 points are important for autocorrelation. The first one is, the first 2 points are pretty much standard, but this one, efficiency and then standard error underestimated, these two are important points. So efficient refers to that their standard error are no more minimum, and then their standard error are underestimated. These are the 2 points which you should keep in mind, that whenever your data would have autocorrelation, the standard error of the estimate would not be efficient, they would have not minimum variance, they would be underestimated. So what will be the result of these 2 points? So this results to affect your hypothesis testing procedure, because what happens when you have the estimated standard error being not reliable, you start doubting the hypothesis testing procedure, because hypothesis testing is based on standard errors, and if standard error is no more efficient, you can't trust your results. So what happens? There is very interesting phenomena associated with autocorrelation as a result of these 3 points which I highlighted, which I would like to explain a bit more in detail. This phenomena refers to spurious regression. So when your standard error are underestimated, so the value is higher, you somehow end up getting a lower value. So what happened? You end up finding a relationship between two variables that are moving together over a period of time but has no relationship between these variables. However, due to underestimated standard error, relationship between these variables if you run the model. Let me show you with some example that will make it more clear. First, spurious regression. So spurious regressions refers to a case when the dependent and independent variables moves together in time, but there is no relation between these two variables. They are just moving together in time, and since they are moving together in time, you run a regression on that and you end up a very strong or a very good fit to your data, but actually there is no relation between these two variables. We call such case a spurious regression. Strong autocorrelation linked to unrelated variables very strongly, and we find a very strong relation or a strong fit between these two variables. We may get a very best fit for our model, but practically there may be no relationship between these two variables. So such phenomena is called spurious regression phenomena, and let me show you some very interesting examples of the spurious regression. Although these models may be very good fit, but actually there is no relation between these two variables. Let me start with the first one. So the first example is that I took from the net. There are very many more examples as well. These were more concrete in terms of having all the information available, so I took that. So this first example is of Egyptian infant mortality rate, and they are regressed on annual gross aggregate income of American farmers and total Honduran money supply. So it's a kind of like you took the infant mortality rate in Egypt. Now Egypt is a country in Africa, and then you got the gross aggregate income of American farmers. So that's the American farmer has nothing to do with infant mortality rate of Egypt, but since during 1971-1990 the infant mortality rate has been declining, and so was the income of the American farmer in the same period, and so was the money supply in this. So these were strongly moving together in time. So when a regression model was fit to it, we find a very high R-square value, a very strong correlation in these two variables lead to a very high R-square value, a very high F-statistic value, and a very good fit model when you just rely on R-square value. However, this D. Watson test shows that there is a correlation, there is a problem of autocorrelation. So although we may conclude based on F statistic and R square that this is a very good fit model, but this is not, this is a spurious regression. Similarly, you can think of US exports index and the Australian male life expectancy. So there is two uncorrelated variable. If you apply a common sense filter, there is no correlation, there is no link between these two variables. However, since both these variables are moving together between 1960 and 1990, so if we took the data for this period for these two variables and run a regression model, we get a really good fit with a very high F statistic value and highly statistical significance, but actually these are not. Similarly, you can see another example, US defense expenditure and the population of South Africa, a very strong correlated, a very good fit, R square 0.94, 94% variation being explained by this regression model. Or US defense expenditure is explained, 94% of US expenditure is being explained by increase in population of South Africa. Does it make sense? Not at all. This is spurious regression. Similarly, total crimes rate and the life expectancy of South Africa. Again, population of South Africa and total R&D expenditure in USA. So you see, you find strange kind of correlations here. You can even link population in your country with the X production in your country, chicken X production in your country, you may find a very good fit for that model as well. But trust me, there is no relationship between these two. So going back to the consequences slide, so we said that we have a problem of autocorrelation when the assumption of ordinary least square of no autocorrelation violated. We get a problem of autocorrelation. Then we studied what are different causes of autocorrelation. So we listed a number of causes of autocorrelation that included the specification error, the lag values, the inertia, the specification error, the Cobb wave phenomena, etc. Then we says that these autocorrelations has a number of consequences for OLS estimators. We says that although the OLS estimators are still unbiased and consistent, however, they are no more efficient, and that efficiency or that minimum variance issues lead to question mark the hypothesis testing mechanism, and we can't trust it anymore. Furthermore, the standard errors are strongly underestimated, and because of that we end up finding relationship among explanatory variables and dependent variables that actually may not be strongly having any or may have any relationship. So we end up having spurious or regressions. That's it for today. See you tomorrow in new lecture. Meanwhile, if you have any questions, please do post it or email me, or you can post it below in comments. I will like to answer. We will continue this discussion in next lecture. Thank you for your time and patience.